Okay, 2:15. Exciting times. We are now going to get started with the Blitz talks. You wonder, how are these models doing so well? Who are the great people who put it together? Now you get to find out. We're going to start off with a presentation from AE Studio. Mike Vaiana, I'm not sure if I'm pronouncing that correctly, is going to be presenting this. So I'm going to turn on recording on my end, and you should be good to go.
Cool. Yeah, thanks, Joel. And you got it right, so congratulations on that. My name, that is. Needs permissions. Please go to operating system browser, settings, grant access. Is there a better way to share my screen?
Other than the button at the bottom of Gather?
Yeah, I'm getting an error saying it doesn't have permissions.
Give me 1 second. Okay, maybe we can like switch orders while we try to work this out. So
that works for me.
Either Maureen or Sean, do you want to try? Whichever you feels like you want to speak first. And also, hopefully, your screen sharing works.
Okay, so can everyone hear me?
Yes,
Yep.
we hear you.
Yeah, so I'll just start the screen sharing. I think I've set it up. Okay, so my name is Maren, and
I'm not sure
while I'm
if you threw that on.
yeah, I'm just setting it up right now, but I'll just like start introducing myself while I do that. Okay, or not. Okay, sorry. I think my computer is struggling a lot, but I think that should work. Does this work?
We see it.
Okay,
Great.
cool. Okay, cool. Yeah, so my name is Maren, and I'm a PhD student at the University of Cambridge. And I'm going to tell you about iLQR-VAE, which is this method that we've been developing in my lab to essentially extract latent dynamical systems from neural data, and that we used in the Neural Latents Challenge. So what I'm going to do here is I'm actually going to go through some bits of this tutorial notebook, which I've made to like present the method. And I'm going to kind of give some like high level overview of the method, and then kind of show how we would go about using it in practice on some example trial from the maze datasets. So I'm going to skip over like a lot of bits of the notebook. So first of all, like if you have any questions as I go along, like feel free to stop me. And also, I guess if you're interested, I encourage you to actually like look at the notebook. And yeah, so I guess I'll get started. I hope my computer doesn't crash as I do this because it seems to be struggling a bit. Anyway, okay, so iLQR-VAE is a method for inferring latent dynamics from noisy time series of observations. And so more specifically, the way it does this is by assuming the following model for the data generation. So actually, can you see my cursor as I'm showing my screen? Or can you just see the screen?
I am currently just seeing your screen.
Okay. Yeah, I don't know how we see the cursor. Okay, well, anyway, I'll just describe what we're seeing on the screen then. So this is the generative model we assume for the data. So in the center, we have essentially this like latent dynamical system. So this latent RNN. And what we do is we assume that this latent RNN is driven by a set of inputs. And so here, when I talk about inputs, I mean both ongoing inputs and the initial condition of the latent RNN, because we assume that we can use the first inputs in the sequence to actually set the initial condition of the RNN. And so then we assume that these inputs give rise to a set of latent trajectories for the RNN in a deterministic manner. So basically, given a set of inputs, the latent trajectories are fully deterministic. And then that these latent trajectories are going to be decoded into a set of observations. And so So here we are looking at like a set of spike trains. So we would have some like linear readouts, and then pass some sort of like factors for nonlinearity and assume some Poisson likelihood for the generation of the observations given the latents. And so this is like the way in which we assume the data is generated. And for those of you familiar with alphads, this is quite similar to the alphads generative model, with some differences. So for instance, the fact that we use a different prior of our inputs, and also that we don't have any bottlenecks between the different parts of the model, although I guess this is something we could add if we wanted. And so then, like, given this, what we're interested in is in learning the parameters of this model. So learning the parameters of this RNN and the different readouts, and being able to perform inference. So to extract, given a set of observations, the inputs and latent trajectories and firing rates that gave rise to these observations. And so the way we do this is by formulating the whole model as a variational autoencoder. So what this means is that we introduce some recognition model. And so basically, we're going to have like the generative model, which gives us the mapping from the inputs to the observations. And then the recognition model gives us the mapping from observations to inputs. And it essentially tries to find the sets of inputs which may have given rise to the observations we're seeing. And the way in which iLQR-VAE really like differs from other methods is the way in which we perform this inference. And so what is typically done in this VAE setting is that people use parameterize this mapping from observations to inputs. And so they use a set of neural networks. And so, for instance, like in alphads, I think they use like bidirectional recurrent neural networks. And that then they basically feed in the observations to these RNNs and get out the mean and variance of a distribution over inputs. And so this is like the typical way to define this recognition model. But it kind of involves adding new parameters to the model, and like new parameters and hyperparameters that you need to adjust. And what we do in iLQR-VAE is quite different. Instead, we say like, okay, like these inputs, we're going to choose them to be the inputs which are most likely to have given rise to the observations given the set of generative parameters we have at this point. And so essentially what we do is we find the inputs as the solution of an optimization problem. And we solve this optimization problem using an algorithm called iLQR, which essentially returns the inputs which are most likely to have given rise to observations given a set of generative parameters. And so one way to think of it is that we essentially define our recognition model as kind of like the inverse of the generative model. And so the nice thing about this is that we don't have to introduce any like additional parameters, and it gives quite a compact model with like I guess fewer parameters, and all of the parameters are like just like tied together through this data generation process. And another advantage is that it means our inference model is very flexible, so you can apply it to heterogeneous data. And so, for instance, you can apply it to like time series of different lengths and to like having like more or less neurons. So this is the iLQR-VAE model, and one last thing to note is that so it's like just like one point I want to make is that it's very nice to have this compact model, but it does come at a cost, which is that this inference goes through like an optimization process, which can get quite expensive if you start using big models. So in that sense, it's maybe not like the fastest method, especially as you start assuming like big latent sizes and having like many neurons. Okay, so this is basically the full model, and so now I'm going to show you how we can use it in practice. So I'm going to go through some bits of the code. And one thing, so I guess you can see my screen. and so like the code for the method is in OCaml, and I'm assuming many of you are probably not familiar with it, but it's like a functional programming language that we use in my lab. And I think the notebook should still be understandable, even if you're not familiar with the language. And yeah, so I still encourage you to go through it, even if you're not familiar with OCaml, because you should still be able to like run everything and like understand what's going on. Okay, so if we're actually trying to fit some iLQR-VAE model, the first thing we would want to do is to actually like define the generative model we want to use. So what this means is that we would want to like essentially define what sort of like prior we want to place over the inputs, and what sort of like RNN we want to use, and what sort of likelihood model we're assuming. And so here we're going to assume some Poisson likelihood because we're going to model some spike trains, and we place a student prior over our inputs, which is like this heavy tail prior, which can allow us to get spot inputs. And we use some small GRU as our RNN. And so yeah, so we've defined our generative model. And so here I'm going to skip over all the like training parts and just skip to assuming we have like a pre-trained model and look at how we would go about performing inference with it. And so we're going to look at performing inference and finding the inputs and firing rates for one trial from the maze dataset. So this is what the data looks like. It's like 182 neurons and 700 milliseconds of recordings, so binned at 5 milliseconds. And so what we're going to do is we're going to here load a set of pre-trained parameters. So we're just going to load this here, and then we're going to look at what the input that best explains the trial looks like and what the firing rates look like. And so, as I said, the way in which iLQR finds the inputs is by essentially like converging iteratively to the set of inputs that are most likely to have given rise to the observations. And so here, okay, so my notebook is kind of freezing, but yeah, hopefully at some point it will execute the cells and plot the inputs. Yeah, sorry about that. I think. Okay, well, yeah, I think Everton is a bit much. Okay, well, I'll kind of assume we can see what's happening then. Okay, so now it's executing it. So, okay, sorry about that. So, like, what you can see is that iLQR converges, so in 14 iterations, to like this set of inputs to explain the data we just saw. And what's interesting about this is that we see that iLQR basically converges to a set of inputs which are confined to the first few time bins, and which are actually confined to this green rectangle here. And actually, this green rectangle corresponds to the inputs which are used to set the initial condition of the RNN, because as I said, we use inputs to both model ongoing inputs and the initial condition. And so this is quite interesting because like it's kind of known that this main dataset is well described by autonomous dynamical systems, but here it's not actually something that we baked into the model. Like we assumed that inputs could come in whenever during the trial, and the model kind of learned on its own that that the best explanation for the observations was like these autonomous dynamics. So this is kind of nice. And if we look at the firing rates, so this is what the firing rates look like. And so this look like, I guess, like fairly reasonable firing rates. And so then so I'm almost done. So before I wrap up, I'll just tell you how we do the cause moving in iLQR-VAE. Because so once we have this, like we're going to want to assess like just how well they describe the data. And so the way to do it in the challenge was to look at cause moving, so prediction of like the these held out neuron firing rates from the held in neurons. And one nice thing about iLQR-VAE is that, as I said, we have a very flexible inference model. And what this means is that what we can do is like during training, we can train the model on all of the neurons. So we can use like the 182 neurons from the training set to fit the like parameters of our generative model. And then at test time, we're going to have only a subset of the neurons available to us. And so what we're going to do is we're going to like hide a part of the readouts that we've learned and perform inference using this partial readout. And then we're going to get inputs and latent trajectories having used this like partial model. And then we can decode them into the full set of neurons using the full readouts that we learned in the training phase. And so the nice thing about this is that it means we were able to train the model using all of the neurons, and so to in a way get like a higher quality inference during the training because we were using more data than if we only trained using the held-in neurons. And I think this is potentially one of the reasons why iLQR-VAE can do like maybe like better than some other methods, that it's really using all of the data in that sense. Okay, so I think I'll stop here. At the end of the notebook, I also have some examples showing how you can use iLQR-VAE to like perform inference on the trials of like different length, so like shorter or like longer trials. But yeah, because my computer is struggling, I think I might not take the risk of going through that. And yeah, instead, like if anyone has questions, happy to answer them, or we can discuss more at the poster session. And also, like if you're interested in the technical details, some of them in the notebook, and we also have like a paper that kind of describes the method in more details if anyone is interested.
That was a really great presentation. Thank you very much, Maria. I was curious if you can comment on, you had mentioned at inference, it can take a little bit longer to infer than maybe some other models that have a recognition network. Could you just like approximately how long does it take to perform inference?
I mean, I guess it really depends like what kind of compute you're using. So I guess for like one trial here, if I'm running it on like one CPU for one trial, it might take like 1 or 2 seconds, I would say. Which yeah, so it's definitely yeah. Yeah, maybe it could be made faster in some ways, and yeah, like it could potentially be like optimized in some ways, but yeah. And it's going to be a lot faster if you use like a smaller latent state, but then that's less expressive. So then there's a balance.
Smaller latent sizes in like a smaller GRU or something like that?
Yeah, smaller GRU, yeah. But, like, yeah, it scales, I think, cubically with that. So.
Gotcha. Thanks.
Yeah.
Great, thanks for the presentation.
Cool.
So we're going to go ahead and try.
Joel, I can't tell if. Oh.
That was me.
My bad. Go ahead.
Yeah. We're going to go ahead and try have AE present again. I will be screen sharing and sort of just like synchronizing with Mike, and hopefully this will go without a hitch. So give me 1 second to get that up, and here we go.
Cool. Yeah. Thanks, Jill, for doing that. So I'm Mike Vaiana. I'm a senior data scientist here at AE Studio. And before I even get started, I just wanted, presentation's gone. Are we?
Joel, I think you're muted if you're trying to talk.
Maybe we could have done a separate run through in the 15 minutes just now. I think what's happening is that my gather automatically disables when I am off screen, and I am just trying to quickly configure that. Perhaps Sean should kick off again, and I can figure out this one more time.
Yeah, sure. That works.
And thanks, Sean, for accommodating.
Yeah, no problem. All right. Okay. Hey, everyone. Today, I want to give you a brief overview of MINT, which is a new decode algorithm I've been developing in Mark Churchland's lab at Columbia University. And MINT was primarily developed for brain-machine interfaces, but it performs neural state estimation in addition to decoding behavior directly. And MINT is a little bit different than some of the other high-performing methods you'll see in this competition, insofar as it's not a neural network. And all told, it is relatively simple. But the performance we've seen is quite good. And there are a number of other benefits to MINT that extend beyond raw bits per spike or velocity R squared. And these things include modularity, low training time, the ability to run causally, and the ability to work well on a relatively small amount of training data. But in order to understand how MINT works, we need to be comfortable thinking in terms of neural states and neural trajectories. And a neural state is simply a vector of firing rates at a single moment in time. So if we were to plot the firing rates of, say, 3 neurons against one another, the neural state would correspond to a single location in this space. And if we consider the neural firing rates at subsequent moments in time, we would see that the neural state moves throughout this space, it carves out some path, and we can call that path a neural trajectory. But the firing rates are not directly observed. The spikes are what we observe, and this whole benchmark is premised on that fact. But we can presume that on each and every trial, there is some underlying neural trajectory. And while we're ultimately interested in single trial neural state estimation, it can be helpful to look at the trial average trajectories where the signal to noise ratio is good in order to better understand the structure of neural activity for a given task. But the key to building any good interpretable model is to make statistical assumptions about the data that accord with the empirical structure of the data. And in our lab, we've been looking at the geometry of neural data for a number of different tasks, and we've seen some recurring motifs in the neural trajectories. So first, the neural trajectories are highly stereotyped and importantly directional, which is to say you only traverse these trajectories in one direction, never in reverse. We see that the neural trajectories don't fill up neural state space. In fact, most of state space is actually empty, yet these trajectories can still have a high linear embedding dimensionality. And finally, neural trajectories can look pretty different for different tasks. So like in a reaching task, the neural trajectories correlate well with reach velocity, which means a linear readout of velocity can do a decent job. But in cycling, we find that the neural trajectories don't correlate with any of the relevant kinematics. And in some tasks, we can have 2 neural states that are far apart from one another that both correspond to the same kinematic state. So we need methods that can respect these geometric observations and handle the heterogeneity in the neural geometry across tasks. And so MINT is really the outcome of our endeavor to build a model with statistical assumptions that would embody these geometric observations. Okay, so how does it actually work? Here I'm showing you 4 neural trajectories, each for different reaches in a reaching task. And we can actually trial average the kinematic variables for each one of these reaches to generate behavioral trajectories that will go along with each of these neural trajectories. So these are just the trial averaged reaches we're looking at here. So each neural trajectory gets its own behavioral trajectory, and each neural state within a trajectory is going to have a corresponding behavioral state. And MINT works by learning these trajectories in training, and then assuming that during testing, the the neural state is always going to be somewhere along one of these 4 neural trajectories in this example. And that assumption actually buys us a lot because it reduces the number of potential neural states from anywhere in this high dimensional space down to a relatively small number of points along these trajectories. And it declares that neural activity evolves in an orderly fashion, and it makes explicit exactly what that order is. So if each of these 4 trajectories had 1,000 neural states, we would have 4,000 potential neural states to consider. And MINT approaches estimation probabilistically, which is to say, of all the 4,000 states here, which one is the most probable given a Poisson model of spiking? And we would then choose that as the most probable neural state and decode the corresponding behavioral state. And this framework may sound a little bit overly simplistic on its own, but it's actually made more powerful and more general by a couple of key extensions. And the first is just that we can leverage a history of spiking activity in a powerful way, because in our model, there's only one way you could have arrived at the present state along one of these trajectories. And so we don't need to marginalize over an infinite number of possible histories. And second, we don't actually limit ourselves to only decoding neural states along these trajectories. Rather, we identify multiple candidate states along the trajectories and then interpolate between them to find the most probable intermediate state. And this allows us to generalize between conditions. So whatever the optimal neural interpolation was, we can go ahead and apply that same interpolation to the corresponding behavioral states. And so in this example here, it doesn't matter that the decoded reach direction wasn't actually in the training set, because MINT identified that the purple and blue states were good candidates and then interpolated between them accordingly. So we can still capture single trial variability as long as that variability is behaviorally relevant and we've sampled the behavior of interest within enough idealized neural trajectories. So really, MINT operates in 2 steps. The first step is to use those idealized neural trajectories as a scaffolding to approximately determine the neural state. And then we use interpolation to locally improve the resolution of the estimate and generalize between conditions. So here I'm showing you those same neural trajectories for reaching, but also reprising the animation from the title slide that contains neural trajectories from a cycling task just to help you visualize the method in action. And the green sphere represents the neural state estimate over time on a held out test set of spikes in the cycling task. And you can see the estimate sticks close to the learned trajectories, and it either loops around the coolly colored trajectories or the warmly colored trajectories, depending on whether the monkey is cycling forward or backward. And these 2 tasks have neural geometries that are quite different, but MINT doesn't rely on the mesh of trajectories adhering to any particular structure, nor do the trajectories have to correlate with kinematics in order to perform accurate state estimation and decode behavior. So MINT can actually work for a wide variety of tasks, even if those tasks have dramatically different geometries associated with their neural data. And the performance in phase 1 of the competition here was validating for us. Here we're looking at bits per spike for each data set from the competition for each method submitted. And there are a lot of methods to compare here, so I'll just break it up into a couple of smaller comparisons. And the first is just comparing to the other simple non-neural network baselines, because MINT itself is not a neural network. And we see that MINT is consistently ahead here, often by a wide margin. But then if we compare to the top performing neural network submissions, there's a few things we can notice. And the first is that the ensemble is consistently ahead. So that's clearly an expressive approach that we're going to hear about in a few minutes here. But for the non-ensembles, there really isn't one consistent winner. And different methods seem to take the lead on different data sets. But all of the performance here is relatively clustered, perhaps with the exception of the smaller data sets, the MC Maze medium and MC Maze small, where we see MINT and the ensemble are doing well, but the other methods struggle a little bit more. But when it comes to reading out velocity, we actually see that MINT is doing quite well and is a fairly consistent front runner across the data sets. And it's worth noting that the competition enforces us all to use a linear readout of velocity to avoid behavioral readouts that compensate for poor neural state estimators, which makes perfect sense. But I do want to point out that we do have a particularly good way of reading out behavior non-linearly via that one-to-one correspondence between neural states and behavioral states. And when we use it, we find that we get a performance boost above and beyond what's plotted here, ranging from a modest improvement in reaching tasks where neural activity correlates well with velocity, to a more substantial improvement in other tasks like cycling, where the neural data doesn't correlate well with kinematics at all. Now I just want to take a brief break from the slides here to show you guys some code and actually run Mint on one of the benchmark data sets here. So I'll go ahead and start by loading up the Area 2 bump data set here and let Mint train and run on the held out trials. And you can see we have to choose some hyperparameters right off the bat, but you can see this section is relatively short. And one of the benefits of using an interpretable model is that the hyperparameters are also relatively interpretable. And so here we simply have to choose where are the trajectories going to begin and end relative to the GoQ in this data set. When we smooth our spikes to learn these idealized neural trajectories, how heavily do we want to smooth them? So sigma is the width of the Gaussian filter there, or the standard deviation. We have to choose our bin size, which is delta, and how much spiking history to incorporate in inference. And that's pretty much it for this data set here. And you can see that Mint has actually already finished. We've got the training time down here was around a little under 6 seconds, and that's on my MacBook Pro while we're video conferencing here. So it really is a very computationally efficient approach, and we see that as really one of the large benefits of using Mint. And if we scroll down, we can see the performance in bits per spike and velocity r squared that more or less tracks what I was showing you in the slides earlier. But what I'd really like to do is just show you, what happens if we play around with these hyperparameters. So here, if we turn sigma up to, say, 50, also change the bin size to 50, maybe use a little bit less history, 400 milliseconds instead of 500 milliseconds, we can rerun this. And the reason that I want to show you this is basically performance doesn't change all that much. So performance is fairly robust to the few hyperparameters that Mint does. And because they're interpretable, for the most part, say you put this in the hands of a clinician who's using this in a brain-machine interface, they could make an educated guess based on the signal-to-noise ratio that the data seems to have. And it would work pretty well right out of the box. And here you can see, it looks like we've lost a little bit on bits per spike in this run, actually went up a little bit in velocity r squared. So there's a pretty broad range of hyperparameters for which this thing works. All right. Now I just want to wrap things up a little bit here on a high level by contextualizing Mint a little bit within a broader Bayesian framework. And so it's common to start out with some prior beliefs, right, about a distribution of neural states. And maybe we have some prior belief about how those states evolve over time, and some likelihood model that tells us for any given state, what is the likelihood of observing particular spike counts. And we can combine these components into a posterior probability distribution over neural states for any particular spike count observations with which we can easily generate a neural state estimate. But the challenge here is in exactly computing that state posterior and maximizing it, something that's often intractable unless we make simple assumptions in the top row, like a Gaussian prior or linear dynamics. And people have explored these approaches, but it does seem like these approaches miss something, that the structure above and beyond what those assumptions simplify. And on the other hand, we have tools for machine learning, like variational inference in neural networks, that allow us to approximate posteriors that are otherwise intractable, which is pretty awesome. But it also comes with an approximation cost, and it may require a large amount of training time or training data to achieve a good approximation. And so what we've done with Mint here is we've really collapsed these top two boxes into one by directly placing a prior over neural trajectories. And critically, we don't just assume any prior, we assume a finite library of trajectories. And this ensures that there's no need to analytically derive the posterior. We can compute it directly for each state because there's so few of them. And so unconstrained by tractability considerations, we can then make principled choices for each module. And we can use interpolation to help provide a little bit of generalization, a little bit of better resolution to help compensate for the restriction to that initial scaffolding, that initial finite library of trajectories. And so each component of neural state estimation in Mint fits into one of these modules. And how we go about learning the library of neural trajectories has no bearing on the stochastic model spiking that we use, or whether we use linear interpolation or some other strategy to fill in the mesh. And with the full posterior distribution directly computed for each state, we're also free to move beyond a simple argmax operation. We can use more general Bayes estimators, incorporate a utility function if that was something that we wanted to do. And if we wanted to incorporate drift correction or use transfer learning from another subject, there's no mystery about how we would incorporate these things into the black box, because it isn't a black box. We know exactly which module we'd want to modify, and in that case, it would be how we learn the library of trajectories. So I'm really excited about MINT because it seems like the mesh of trajectories is a good match to the geometry of neural data for a wide variety of tasks here. And it's a fast and scalable approach, but moreover, it opens us up to a principled framework where we can focus on different aspects of this problem in isolation and build up more modular latent variable models and more modular decode algorithms for brain-machine interfaces. And that's what I've got for you.
Oh, it's a pretty awesome presentation.
Thanks.
Great work, Sean. That was awesome.
Cool. Yeah.
I'd venture to say that was the only method that could be live demoed in a Blitz talk.
Yeah.
Amazingly low computational resources. That's super impressive.
Thank you.
Okay, so I'll try this one more time with AE Studio's presentation, and the kinks should have been worked out. So I'm just going to start screen sharing, and I can go for it.
Yeah, cool. Thanks. Hopefully this works this time. So, uh-oh, it's gone. There we go. It's back. Yeah, so I'm Mike Vaiana. Nice to meet you all. I'm a senior data scientist here at AE Studio. And before I get started, I did want to thank the organizers of both the benchmark and this workshop. It was really fun for us all at AE to participate in the benchmark. And I think most, if not all of us, are here, going to be here at some point today during the workshop. So thank you so much for doing that. So just quickly, what is AE Studio? So we're a product development and data science consulting firm. The AE stands for Agency Enterprise, as in human agency. And AE really believes that technology should increase human agency. And that might just seem like a tagline, but it really is actually core to how AE thinks and operates. And it's something that I really like working there, and something that I'm proud of to say that I work there, that they really stick to that. And why are we in this competition? Well, we're working to build software to support BCI research. And if you want to learn more, I'll just kind of give you a teaser. You can check out the links at the end of this presentation and learn more about what we're doing there on our website. And on the right is the BCI team. Not all of us were working on NLB full time, but we were working on it when we could. So there they are. And feel free to reach out and say hi to any of us as you see us around. Okay, next slide. So a lot of you we've already talked to at the poster session, or maybe you've read the poster or our write-up. So you know that our solution is based on the neural data transformer. So just wanted to recognize Joel and Chetan for doing an awesome job with the paper, and in particular the open source implementation, which we forked and used. So thank you very much, both Joel and Chetan. Next slide. Okay, a little bit on our approach and process. We actually think this is one of the key things that we did well, or that we do well in general, and in particular that academic labs can potentially learn from. So everybody on the BCI team comes from academics. We all have PhDs, but now we're all obviously in industry. And we find that following best practices in data science, in particular when you're thinking about delivering machine learning as a product, and when you're thinking about doing software development, in an agile manner. We think that both of those things actually help us accelerate the pace at which we can achieve goals, and also make it much easier to share our work. So I don't want to say too much, dwell on this, but you can read our approach. There's a link at the end of these slides. But just a little bit about what did we do? Well, we scoped out the benchmark and what we thought we could do, and we realized we probably didn't have time to do something novel from scratch. But we did think that if we could find some good open source code from a paper, preferably one from that we knew worked well, that was already a benchmark on the leaderboard, then we thought that we could probably make some improvements on that and ideally get towards the top of the leaderboard. And what did we realize? Well, when we just thinking on the data science best practices side, or just from the data science side in general, we realized that a lot of data science competitions are won by ensemble models, because when you ensemble models, you tend to get some increased performance. And we also realized that when we started looking into what was out there, that in particular NDT implemented a random search, and we thought that just adding a smarter search could get us some lift too. And we identified those as really lower time cost, easier to implement, but very likely to give us lift. And so that's what we went for. So next slide. So our method, I kind of already gave it away. We used the neural data transformer written by Joel and Chetan, and they have a paper there and open source code which we forked. The meme in the top right is relatively how we felt. It was written in PyTorch, which we like. Obviously it was a great paper, good GitHub link, and it was pretty easy to get up and running. We had to do a little bit of hacking to get it to work for us, for our purposes, but really not much at all. So great job there. And then what I'm showing in these charts on the bottom left is the x-axis is the masked loss, and the y-axis is the competition metric, the co-BPS on the validation set. And the x's are individually trained models. And so what you might expect is a really strong negative correlation between the co-BPS and masked loss, but that's not exactly what we see here. There's a regime where, the masked loss is maybe not as low as it could be, but the validation co-BPS is still pretty high. So that's kind of interesting just to note. And then on the right side of the screen, you see the x-axis is ensemble size and the y-axis is co-BPS. And in blue, we did actually run a random search, and we also ran a Bayes ops search. And so in the blue is the random search, and then the orange and green, the orange is Bayes and the green is Bayes plus random, just including everything. Those track pretty closely, so you can just blur your eyes and think of that top line there as the Bayes search. And what you see is, this idea that ensembles help performance is, pretty clearly shown, that the second you even do 2 or 3 models in an ensemble, you get a pretty big performance lift. And this chart just helped us be confident that the score, our final metric, wasn't super sensitive to the size of the ensemble, so that we could pick the maximum performance size, and it wasn't going to we weren't extremely overfitting to that. So that's our method. Next slide. So I know, Joel, you have a talk on this, but I just wanted to give an idea of NDT really quickly, because I think that we had some ideas for improvement that we didn't have time to do that maybe somebody could pick up and run with. So when you think about the neural data transformer, it's a transformer encoder, and the inputs are population neural activity over time, and the outputs are an encoding per time step. And then the final rate predictions are a single learned matrix times the encoding vector to give you your output rates for your holdout neurons. And when you think about what this is doing, you have to predict the entire holdout population output rates. So the transformer really has to learn to encode into a single encoding vector, all the information it needs to be linearly read out to get your output rates. So that kind of seems like, I mean, it works, and obviously the ensemble works really well, and it's a great model. But maybe how can we improve it? It kind of seems like a lot to ask the architecture to linearly read out the entire population of rates for every single time step. So a way that a possible improvement, just one, there's a lot that we've thought of that didn't have time to implement, and we don't know if they'll work, of course. But if you're looking for something to do, one way to think about this is actually just do the entire transformer stack with the decoder and think of it as like a seek-to-seek model. And Joel and Chetan, if you tried that, or if you even tried it and it's in the paper and I just don't remember that, then let me know. That'd be super interesting. But that's something that somebody certainly could try. And then the intention mechanism will run over the entire encoding dimension in the decoder stack. So instead of having to figure out your population activity from a single time step, it can learn to pay attention to the right time steps to figure that out. So that's one thing that, just one, I don't want to say simple, but one, next step that somebody could try if you were looking for something to do. Okay, next slide. A few things that didn't work for us. So auto LFADs obviously works great because it's on the leaderboard, but we tried to re-implement it and we weren't able to reproduce or beat the leaderboard results. And we also, even when we tried ensembling our LFADs implementation or adding it to the NDT ensembles, it didn't give us performance improvements. So that could just be a poor implementation on our side. We're not totally sure, but we thought it was something we would report. We also tried stacking. So instead of just, our ensemble, by the way, is just an average of the output rates. So stacking is another type of ensembling where instead of averaging, you actually learn a model on top of your outputs. And that didn't work for us. And that's kind of interesting because, our ensemble solution is in the space of solutions of our stacking models. So it didn't find a solution that was that good. So we didn't have a ton of time to try stacking, but and we think that we likely didn't regularize our stacking models enough. So that's something that you could also try in the future. It didn't work for us, but there's a lot more that could have been tried there. And then we also tried per neuron ensembles, and the idea here was that each model may be potentially, in order to reduce loss, specializing on a subset of neurons. And so maybe a single model is like particularly good at predicting the holdout units for some subset of them, but not across the entire population. And so we tried taking the top K many models per neuron and ensembling those, and then interleaving those into a final rate prediction. And initially it looked really promising, but it really didn't hold up on the test set. So we likely, again, overfit there. But there may be other things that you could try along those lines, particularly better regularization or fitting them in a different way where you're not just reuse the validation set to fit this, but that probably led to overfitting. So there are some things that we tried that didn't work, just so you're aware if you're out there trying things. And next slide, please. Yeah, and so kind of a final message here is that we are hiring. We're hiring BCI data engineers and data scientists and others. So if you're interested, there's a link right there, AE Studio, join us. And then also we're exploring a range of academic collaboration. So if you're interested in that at all, feel free to reach out to any of us on the team, but Diogo has offered his email, so you can reach out to him, but also feel free to talk to any of us. And I think that's it. The next slide is just a bunch of links if you're interested in learning more. Thanks, everybody.
Thanks, Mike, and the rest of the AE team. That was naturally a very flattering presentation, but I thought it was awesome the number of different kind of like other experimental branches you tried out. It was I think like you called it like kind of quick and efficient, but like each of the different directions I thought were substantial efforts nonetheless, even if it was not at the level of like model building. So.
Yeah, that's maybe I should have said a little bit more about that, but you kind of opened the door for me here real quick to respond, which is, yeah, some of the things that we think about when we're delivering machine learning, there's a whole product side where you have to deploy it for users, and obviously you don't need to do that in research, but there's still a development side where you want to build like really robust data pipelines and start small and iterate quickly, and that's the approach we took that allowed us to experiment quickly. And so that's kind of an elaboration on what I was saying, that if you adopt these best practices, you can really accelerate the pace you can do research or just accomplish your goals in general when you're writing software, particularly in the machine learning space.
Mike, that was a really great presentation. I was just curious if I'm not sure if it's in kind of your repo or your kind of approach document, but maybe you might say like the degree to which there's like backend infrastructure that you found helpful to be able to kind of like test your models in an organized way and evaluate results rapidly and iterate and et cetera.
So for backend infrastructure, we used AWS and we used RayTune for experiment, hyperparameter tuning. But actually, and the approach that we took, and this is a little bit of what I was just saying, is that we actually built strong data pipelines and right, like we actually built tools on top of the NLB tools so that we could easily plug in a simple model or plug in any model into the middle of that pipeline. And we actually started with very simple models. I think the first model we did was a Poisson regression, just testing it, right? And then we iterated from there, and we tested some custom simple PyTorch models in between, and then eventually we plugged in NDT in the middle there. So that was what allowed us to iterate quickly, and that required, I think we ran everything on AWS, but we didn't have to run on like large instances to do that, like really small, cheap ones at first. And then, we swap instances all the time. We need to run an experiment, take a lot of compute power, pay for it, and shut it down, go back to a small instance and iterate. And so, yeah, I hope that answers your question.
Yeah, it absolutely does. And I was wondering if there's also kind of a layer of, as you're running these different experiments and kind of tracking what works well, like maybe not hardware infrastructure or more like project tracking or management that you found helpful.
I see. Yeah. So on the project side, we happen to use something called Pivotal Tracker, but more generally, that's just an implementation of a thing that tracks like an agile software setup, right? So we have tickets and we have stories, and we project manage those, and we keep them small and curate them. So that's on the project management side, and then on the tracking side, we used RayTune for our tracking. So we kept all of our experiments, like all of the metadata there. We used RayTune for that, but we have used other tools in the past, in particular like MLflow as we've used. I think we've played around with weights and biases, but I don't think we use that too much. Yeah.
Awesome, thanks.
Sure.
So that was the last Blitz talk. Now we are a little bit in, but like we're basically going to move into a poster session. If you have further questions for any of the existing presenters and or have questions on any of the resources that were kind of like provided, find the relevant poster, find the relevant presenter, and go ahead and chat them up.
Before we all break out there, I just want to officially thank the presenters. These are, I think that this is kind of like amazing. All of you have done a really great job, explaining your methods and kind of making everything accessible. And I really think, it's a critical step for the field, not only as we tried to make the data and metrics accessible and that sort of thing, but like having models that we can all build off of is really going to drive progress. So this is really wonderful to see. And, there's a huge team kind of organizing this stuff, but I just want to explicitly call out thanks so much, Joel and Felix, for all their hard work in getting this workshop together. And it's wonderful to see everybody. So yeah, let's enjoy the poster session, and we'll all be around for hacking hours and stuff.